So for homework, what I'd like you to do is do the other independent sample. You don't need to run this with SPSS, but simply look at C here. What would happen if the organized word list, the recall was 3, 4, 5, 6, and 7? I printed out the results from that on the bottom screen with the P equals point, or sig equals 0.347. See if you can write out where all those terms come from, if that's significant or not, APA statements, and real-world conclusion. You can probably figure out what's going on there pretty easily. The last main new topic I want to cover tonight has to do with a slightly different way of looking at things. And so I'm going to ask, on the last page of the agenda, there's something called an analysis of variance. And Drew, do you remember what that term variance means?
It's a measure of dispersion. So
Yeah, exactly. It's a measure of dispersion, and there's a slightly different way that we can actually do something called an analysis of variance. It's a little bit unique, and I want to show the class kind of how to do this. And so we have the situation here, and it's a very simple situation. Again, I'm interested in assessing if a new drug helps with memory. 3 people get the drug, and they recall 5, 6, and 7 words, and 3 other people do not, and their recall is 1, 2, and 3. Now, Drew, can I ask you, Emily, do you need to go somewhere else?
It's
Drew,
freezing out there.
Drew, can I ask you, is this an independent sample design or a repeated measures design? It's independent sample. We're only testing people one time here. And so in this particular case, it's an independent sample. How many independent variables do we have here, Drew?
Just the one.
Just one independent variable, and how many levels? 2. Now you could do a t-test on this, but I'm going to actually show us how to do a analysis of variance, because it's a little more of a general thing. And people, have you ever done an ANOVA?
Yeah.
Yeah, it's much more used in a lot of.
Still scared.
But we're going to do a simple example here. So what I want to reflect here is that the ANOVA, the guy who created the ANOVA was a guy called Fisher. And that's why you get at the end not a t-score but an f-score. So it's an F ratio. Look what it actually says there in B. That the F ratio is composed of the variance between groups over the variance within groups. Now think back, Drew, to what we had before. The variance between groups. Do you remember what the numerator was in a t-test?
The difference of the mean.
The treatment effect.
Right.
Exactly. So the numerator here, if you want to write it down with the variance between groups, that reflects the treatment. Do you want that to be large or small?
Large.
Large. The denominator is now called the variance within groups. Before, that reflected error, right?
Okay.
And you wanted that number before to be what?
As small as possible.
Small. It's going to be the same thing here. The numerator is the treatment effect. The denominator is the error. And we want the numerator to be large and the denominator to be small. Now, if you go to the picture file, I'm a terrible artist, so I decided it would be best to do this out, scan it in, and I've been doing this every semester. Take a look at the graph there. If you look at the graph, I've actually done a little figure. I've got the 3 people with no drug. I hope I did this right. Yeah, 1, 2, and 3. And the 3 people with the drug. Does it have 5, 6, and 7 there? So what I did there is a little schematic of the 2 sources of variance. Notice the line that says variance between groups. Where does that line go from?
The means.
The means. So the variance between groups, the numerator reflects the treatment. Do you want that number to be large or small?
You still want to be large.
You want it to be large if you want to find a significant difference. And so here the numerator is simply the variance between groups, and that's the 6 and the 2, kind of the same thing it was in a t-test. The denominator. Notice what I have for the denominator. It says variance within groups. It's the spread of the scores within a group. Now, if you think about it for just a minute, if I give 3 people the drug, the mean there is 6. Do I want one person to have a 0, another person to have a 6, and a third person to have a 12?
No.
No, because there'd be a lot of
It'll be binary.
dispersion, a lot of error, right?
Right.
So the variance within groups reflects the spread within a group here.
Okay.
And so variance within group, you have to get the variance within the 5, 6, and 7 group. Do you want that number to be large or small?
That's too small.
You want that to be small. You also have to get the variance within groups of the 1, 2, and 3. You want that to be small as well. So that's kind of the visual schematic, the only picture I'll have this semester of things. Does that make sense, though, with this simple example?
Yeah.
So with that being said, let's go back to the outline on the F ratio. The F ratio, we said, reflects the variance between groups and the variance within. The numerator reflects the treatment. The denominator reflects the spread of the scores within groups, the error. Now notice the different F scores I can get. Let's say you do some computations and your final F score is equal to 1. What would that say about error in treatment?
Equal.
That's exactly the case. That if you get an F score of 1, that would be saying that the treatment effect is the same as the error. Is that good news or bad news?
Bad news.
That sucks.
Horrible.
Because it means whatever you did is equal to the error. So if you get an F score of 1, do you think you'll be significant?
No.
No. So an F score of 1 means your treatment effect equals your error and it won't be significant. What if you get an F score less than 1? What would that say about error in treatment?
Not sure. 1 and 2 are negative.
It would mean you have more error
Oh, but it'll be a ratio.
than treatment. Would that be good news? No, that would also royally suck. So if you get an F score less than 1, that will never be significant, because that means you have more error than treatment. What we want is we want to get F scores kind of large, right? The larger your F score, the more the treatment is bigger than the error, and then that's going to tend to be more significant. So we want large F scores. Does that work then? Okay, we'll stop that way.